Hi, this demo is to demonstrate about image compression decompression using JPEG pipeline. This is something which I implemented as a part of the assignment. I implemented a JPEG encoder decoder to decompress a given .rgb image. The image which were given to us for this assignment were all .rgb formatted images, which means that this particular image had three channels: red, green and blue. Now we'll discuss about how I implemented JPEG encoder. What are the steps which are performed in an encoder? So far, we know that each image is a .rgb formatted image, so it has red, green, and blue channels. So we separate out the channels of the image and we divide each of these channels into chunks of 8 into 8. So, for example, say if the size of the image is something into something, you divide that by 64 and you would know the total number of blocks for that particular image that you would be creating. For each block, then perform a discrete cosine transform. Why? Because you need to transform the image from a spatial domain into a frequency domain and then compute the DC and AC coefficients. On obtaining the DC and AC coefficients, we quantize the DC and AC coefficients with a uniform quantization table. Now this uniform quantization table, it's a standard which has already been provided by the JPEG standard that we need to use this particular quantization table, but in our case we used a separate quantization table which had uniform values in each and every block of the table, and the size of the table would be 8 into 8, which is the size of the block. And when you get the output, when you get the quantized values for each of these channels of each of these blocks, that would be nothing but the output of the encoder. Now we jump to JPEG decoder. We perform dequantization, which is an inverse operation of the quantization. Definitely, as the name suggests, decoder is nothing but performing everything in reverse of which we performed for the encoder. So first step is we perform the dequantization. Whatever formula we apply to get the quantization table in the encoder, we just do the reverse operation of that to perform dequantization. Then we do an inverse DCT on the dequantized AC and DC coefficients to recover image block signal. The recovered image is of course with some loss depending on n. Now, with this particular assignment, we can provide 7 different quantization levels and it ranges from 0 to 7. So, lesser the level of the quantization, less data will be lost when you decompress data and show it on the receiver, and more the level of quantization, more data will be lost. So n is the factor which actually determines how much data is lost while performing this particular operation of compression decompression on that image. Along with this particular thing, also implemented something known as modes of encoding decoding. There are various modes of encoding and decoding coupled with latency. Latency is something which helps us to simulate a network-like environment with that particular image being sent on different bandwidths. Now, different latency would indicate different bandwidths on which you are sending the image. The lower the bandwidth, the larger would be the latency. The higher the bandwidth, lower would be the latency. We will see that when we actually see the demo. There are basically 3 modes. One is the baseline mode. What do you mean by the baseline mode? Here we decode the first block. As we know that we had divided the image into different blocks, we keep that thing when we actually decode it as well. So we decode the first block, we display it, and then we sleep. Sleep is nothing but a technical term which is used to simulate latency. Then we display the second block after decoding it and we display it, and so on and so forth. The total number of blocks are then displayed to display the entire decoded or decompressed image. The second method that I implemented is progressive mode. using spectral selection. What does this mean? We decode all the blocks using only the DC coefficients and set rest to 0 and display it, and then sleep, that is nothing but the latency, comes into the picture. Then we decode all the DC and first AC coefficient and we set rest to 0, and so on and so forth. For all the AC coefficients, till we display all the AC coefficients, we keep on doing this thing. And this is the way we actually get a spectral selection, a progressive mode of displaying your image on the receiver side. We'll look into that thing. And then the third thing is progressive mode using successive bit approximation. In this, we decode all the blocks using the most significant bit first of all the coefficient. Then we go into sleep mode, that is the latency comes into picture. Then we decode all the blocks using the most significant bit and the bit which is next to the most significant bit, that is ms-1, and for all the coefficients, and we display it. And then we again go into sleep, that is latency comes into picture, and then these things carry on till we have displayed all the bits of all the coefficients, and you get the actual image which you want to display on the user screen. Now this is the entire code where the encoder, decoder and everything is implemented. As you can see, this is where we perform the TCT, this is where we perform the quantization, then comes the decoder where we perform the dequantization, and then we perform the inverse DCT. And this is the baseline mode where we perform the baseline mode in order to display it block by block. This is intermediate display which is used in the progressive spectral mode selection, and then comes the progressive mode, bit progressive mode. We'll look each and every one of them. Before that, we need to go to the run configuration, and I'll explain what actually does this. Here we are accepting 4 command line arguments. So the first argument is the name of the image that we want to compress and decompress, or basically perform this operation upon. The second one mentions what is the quantization level, as I specified earlier. If the quantization level is towards 0 or it's lower, then less data would be lost during the entire process. If it is towards 7, that is the highest value, more data would be lost, which would cause a kind of a blurred effect on the image. Then comes our mode selection. 1 indicates baseline, 2 indicates progressive mode using spectral selection, 3 indicates progressive mode using successive bit approximation. And then the last one is nothing but the latency, which is used to simulate different bandwidths. In this case, for the time being, I am doing it once so that we can have a look at the output as quick as possible. And we'll start off with quantization level 1, and then I'll give an example of quantization level 7 so that you would understand what difference does it make. Let's say run, and we are doing it in the baseline mode. As you can see, the block by block it's getting displayed and the entire image got displayed. And as you can see that the blurriness, it's almost kind of you get the same image after compressing and decompressing it on the receiver side, because the quantization level is set to 1. This is one of the modes of encoding decoding. We'll look at the second mode, that is progressive mode spectral selection. As you could see, initially all the DC coefficients would come up, so you get a kind of a blurred image, and then the image starts getting better and better as all the coefficients are displayed at a time for each and every block. This process takes a little time because this particular entire thing happens on the run, on the fly. The image is getting better and better as more and more AC coefficients are decoded and displayed. This is the second mode. I would stop here because it will take a lot of time, and then we'll go to the third mode. As you can see here, initially the entire image would be black because we are just displaying the MSB, and then more and more bits would be displayed for each and every coefficients of each and every block. and it would start getting better and better as the number of as the bits are getting displayed for each coefficient of each block. Guess this is how you would understand what actually I tried to implement here. And now I would like to show one example where I would make this particular value to say 7 or probably say 6, and I'll make it a baseline and you would see the difference. See, as you can see, there is blurriness right here, there's some blurriness here, you can see the block effect. This is because of the loss of data. This is because of the loss of data, and this is because we have given the quantization level to be 6. I guess you got the overview of what I have tried to implement here. Thanks a lot. Thank you.